Hello, and welcome to Solving Electromagnetic Challenges, an EMA webinar series. My name is Matt Miller, and I'll be your host for today's presentation on validation of EMC Plus versus experimental measurement in an EMC lab. Please use the Q&A feature to submit any questions during the presentation. At the end, we will address any submitted questions. Our speaker for today are Dr. Tim McDonald and Zach Stevens. Tim is the president and co-owner at EMA. Tim currently serves as a product manager for Ansys EMC Plus. He supports Ansys EMC Plus users around the world from multiple industries. Tim holds a PhD in applied physics and applied math from Columbia University in the city of New York. He previously led consulting engagements for NASA and DoD major primes pertaining to specialty engineering of critical systems, development of novel solutions to electromagnetic compatibility problems, and in the execution of major programs that require verification to electromagnetic environmental effects. Zach joined EMA as a scientist last year and has since worked on projects involving printed circuit boards, antenna design, and lightning zoning. Zach graduated from the University of Virginia with a bachelor's degree in astrophysics and is interested in continuing to pursue more space-related projects while at EMA. Without further delay, I give you Tim and Zach.
Thank you very much, Matt. So one of the big things that you have to do if you're developing a product of some kind, an electronic device or some type of vehicle, is to meet EMC requirements. In recent years, there's been increased use of simulation to reduce risk going into EMC testing, and in some cases, even the ability of using simulation to replace certain types of EMC testing. In order to increase the confidence in the use of simulation, there's great interest in comparing the results from EMC simulation of devices and products to the results you get in an EMC qualification test. So it's not always an apples to apples comparison. So it does take some effort to make sure that you can compare those two values. In order to achieve some of those validations, we took the time to fabricate our own non-proprietary devices and have them tested. And they were tested with our partner at NIAR, which is the National Institute for Aviation Research at Wichita State University, which is a full-fledged product certification laboratory, largely serving the aerospace community, but open for a wide range of electromagnetic environmental tests, as well as other types of environmental qualification tests. So this is the first that will ultimately be a series of webinars. As we perform more validations, we'll continue to roll out those results so that all of you can have access to them and utilize what we learned for your product design challenges. All right, I'm going to pause sharing for a moment. I can't get my slides to advance. All right. So I want to give some background on the team at EMA, myself and the other technical leaders that contributed to this validation. The EMA team has 45 years of experience in electromagnetic compatibility and electromagnetic environmental effects. We have more than 50 technical staff, maybe 70 total staff. Among those staff are PhDs, FAA designated engineering representatives with the authority to sign for the FAA, as well as subject matter experts in various areas of electromagnetic effects and plasma effects and related items. In the past, some of the past performance included things like DoD development programs, NASA human spaceflight programs, including the Orion program, as well as civilian airworthiness certification, FAA certification, like the Airbus A220, of which EMA had a large role in achieving the electromagnetic effects certification. Automotive EMC is one of the fastest growing areas at EMA, as well as is consumer electronics EMC for devices. All right, so EMA is organized in an interesting way where we have consulting services, test services, and we develop commercial simulation software that we sell through our partner Ansys. So we believe that there's benefits to having capabilities in consulting, testing, as well as simulation for our customers. By having a consulting services team collaborate with our software development team, that means that we generate experience on real industrial problems, which helps us build better simulation software that is commercially available. By having a testing services team, for example, the heart of this webinar is validating simulation using testing. So validating the software is a big benefit to having test services and a simulation team in the same group. Finally, there's certainly importance in having a test services team and a consulting services team because our subject matter experts do more than just execute test plans. We actually have expertise in certification and product design so that we can help tailor testing and help ensure that product designs will meet the test requirements. So we do more than just turn the crank on standard tests. What are some of the tasks that we do? For example, customers may approach us for design review services. They are accessing our subject matter experts with decades of experience. We may do things like review printed circuit board designs, look at the requirements that you're levying on your product that you're developing, and possibly tailor them to proper match the concept of operations or the environment that product will be in. And that sometimes requires collaboration with the ultimate customer or certifying authority for that tailoring, but it requires deep expertise to do that well. EMA is a DCSA cleared facility and staff, so we can work on DOD types of projects, as well as we can serve as the EMC lead for consulting services. There's many cases where our staff serve as an EMC lead, an E3 lead, a lightning lead. Those are common things we help customers when they need a greater level of support and they don't have the internal team to do what they want to do. We are also the team behind EMC Plus and Charge Plus that are on the Ansys product portfolio. And these are flagship products with multiple Fortune 500 customers that they're using to analyze their products. And these two products together are the fastest growing products in the Ansys portfolio. So there's certainly been wide adoption of these tools. Our team does offer simulation services. Let's say customers don't have the time or the expertise to purchase the software and use the software themselves. EMA staff members can provide those services for full device simulation, full vehicle simulation, or to do what I'm going to talk about today, validation versus testing, or sometimes we can provide qualification by simulation when customers ask for that. And then finally, of course, we provide testing services, but sometimes testing services does not mean just running the tests. There are often times that our team will write or tailor test plans, provide custom test services, and quite a bit of our testing, especially full vehicle testing, has an on-site component where we can bring equipment to the customer site. Okay, let's talk very briefly about what we do to tailor MIL Standard 461 requirements. MIL Standard 461 is a military standard that levies electromagnetic compatibility test and design requirements on units. It is widely adopted by DoD procurement authorities. However, it is not a one-size-fits-all document. You can imagine that the inductance of a very long power distribution cable on an aircraft carrier is going to present a very different inductance than a short cable on a small satellite. So it's very important to tailor those MIL Standard 461 requirements to your platform and concept of operation and operational environment, and to closely collaborate that with your customer. However, sometimes making that tailoring requires deep industry experience, and some customers don't always have that on internal teams. So EMA can help with those cases. So examples of tailoring might be spectrum analysis. We can look at what the intended RF systems are in the platform and put the correct notches in the to account for that. As I mentioned before, the inductance of the LISN should consider whether or not you're on an aircraft carrier or something small, as well as if you have special requirements like EMP or lightning. You do not want to levy a lightning requirement on a design that's not going to see lightning, because it will drive weight, cost, and complexity to your design. And our team has extensive experience over decades tailoring and levying requirements for DoD NASA primes, although increasingly we're doing that in the commercial realm. There's two simulation technologies from EMA meaning that we develop them. However, they are commercialized fully through Ansys. So the only place you can purchase these two products is from Ansys or the Ansys channel. Ansys EMC Plus is a platform level electronic modeling and simulation tool that delivers design to validation workflow for EMC. The goal is extreme geometric complexity for full devices and full platforms to give you the shortest time to value. Ansys Charge Plus, on the other hand, combines electromagnetic solvers, fluid solvers, particle physics solvers for easy-to-use multi-physics simulation. It is a tool for plasma modeling and things that involve plasmas like arcs and discharges. And it is all about extreme multi-physics of electro, fluid, and radiation effects. So those are the two products that are available from us through Ansys. A big thing that I have to note every time I talk about the products these days is in the last year, there's been a big change. We've added GPU acceleration to the tools, specifically the FDTD solvers in EMC Plus and Charge Plus. They're on the order of 18 times faster, and you can scale to even greater speeds with larger and larger GPU hardware, for example, multi-GPU hardware. And we've got some new benchmarks showing how good that can be. For example, on full printed circuit boards, it's 16.7 times faster in a GPU versus a CPU. And then a full car is something like 11.9 times faster on a GPU versus a CPU. All right, with that, we're going to shift gears and we're going to talk about some real validation of real measurements. As I mentioned before, EMA chose to fabricate some devices, and these are devices that we own the design, not because we wanted to manufacture electronics, but rather so that we could publicly talk about them in forums like this. So the printed circuit boards and the electronic designs, we have all of the design information for them. We're able to excite them and then test them with our partner that I mentioned before, the National Institute of Aviation Research. And the goal here is to optimize the correlation between simulation and testing so that you can understand how to use simulation so that we can show good correlation so that people can have greater confidence in the use of simulation. But also the way we're testing in some ways is a little bit different. Some tests, such as radiated susceptibility, this is essentially a pass-fail test at each frequency. So there's not typically a measurement done in radiated susceptibility. You're exposing your device to that environment, but you're not measuring what that radiation is creating in terms of voltages and currents in the device. So in this case, we've modified this test procedure to be more analytical in its measurement, and that's allowed us to do this validation. I'm very happy to be joined today, as we mentioned earlier, by Zach Stevens, who did some of this very good work on radiated susceptibility. So I'm going to pass the baton to Zach to talk through some of the results and what they mean for radiated susceptibility of a few devices.
Great, Tim. Thank you so much for that intro. For going over everything. It was a great overview of a lot of other stuff we've done too. So as Tim mentioned, I'm going to talk a little bit about the validation campaign we did specifically for radiated susceptibility. Tim is going to talk a little bit later about radiated emissions, but I'm also going to mention them a little bit in this section as well, because both radiated emissions and susceptibility are closely tied together in concept. And I'm going to talk about radiated susceptibility, particularly with some models that we, as Tim again said, created regarding printed circuit boards and then a set of cables as well. So further, for models of PCBs and cables, it is important to be able to accurately represent how they radiate when excited by a source. So that's the radiated emissions. And then also to understand how they react when placed within an external electromagnetic field. So that's the radiated susceptibility we'll be measuring. It's important to be able to cross-correlate between these physical measurements and the EMC Plus simulations that we have done. So Tim introduced the National Institute of Aviation Research, NIAR, and we went out to their testing labs to correlate some of the EMC Plus simulations that we ran and cross-correlating them with physical measurements. So, Tim, if you want to go to the next slide, the first model that we're going to look at that we've done an extensive amount of testing on is a patch antenna. A patch antenna is a very simple printed circuit board that resonates at one given frequency, although of course it resonates at higher frequencies as well, but it's designed to resonate at 1. The physical model is shown here on the right, and the label on it is perhaps a bit misleading. It says it resonates at 2.5 gigahertz, but in fact, after measurements, we found that this model resonates at 1.7 gigahertz. You can see our EMC Plus model for the printed circuit board for the patch antenna on the left here. You'll see that same trace on the top, the dielectric, and then our antenna port is on the right. It's a little difficult to see in the EMC Plus model, but that allows us to both excite the trace and measure radiated emissions, and then further to measure the signal received on the patch antenna once it is placed within an electromagnetic field, thus allowing us to measure the radiated susceptibility. Tim, if you want to go to the next slide. So the first thing we needed to test was, again, to confirm that our model in EMC Plus was radiating at the correct frequencies. I mentioned that the physical model was resonating at that 1.7 gigahertz. And to test that, we measured the scattering parameters of the patch antenna. The scattering parameters measure the input loss of the signal used to excite the trace. So if the patch antenna is designed to resonate at that 1.7 gigahertz, the signal input into that printed circuit board is going to reflect back the least at that first resonance. And that can be seen here at that first 1.7 gigahertz frequency. When we ran our scattering parameter test on the printed circuit board that we modeled in EMC Plus, we found that that first resonance matched almost perfectly in both frequency and magnitude, getting within 3 to 4 dBs of our desired result and of our physical physical measurement of the actual patch antenna. And even in further higher frequencies, we see that the frequency range response matches remarkably well for the simulation in EMC Plus matching the measurement we did at NIAR. So this was very promising that the printed circuit boards we're measuring are emitting correctly. And furthermore, that allows us to measure the radiated susceptibility correctly. Tim, if you want to move to the next slide. To explain that, because of the reciprocity of antennas, the way that they emit signals should match the way that they receive signals. So if it emits well at 1.7 gigahertz, it should receive the most power at 1.7 gigahertz as well. So to confirm the S parameters then means we can move into radiated susceptibility measurements. And this setup is shown here. The physical test setup at NIAR is shown here on the left with a horn antenna sending an electromagnetic field towards the patch antenna, which is oriented upright about a meter away. We hit it with a constant electric field and then measured the power received at the port. And this is the same setup is shown here on the right in EMC Plus. You can see we have a plane wave that is being sent towards the patch antenna, and then at the base, at the port of the patch antenna, we will be measuring the signal received by the patch antenna from the electric field. So that's shown on this next slide here. If you want to move to the next slide, we can see that throughout the full frequency range, we actually get a remarkably nicely matched trends throughout, especially at that 1.7 gigahertz primary peak. We see that we're within just a few dBs of the measured results. And then throughout the rest of the frequency range, we get nicely matched frequency responses. We're working in further measurements of this validation campaign to understand some of the uncertainty on both our physical and simulated measurements. But this is a really promising start to show that we are able to accurately understand the frequency range response just from a time domain simulation that runs very quickly. So we can run a fast simulation and get a full comprehensive understanding of the frequency range response of the printed circuit board with its radiated susceptibility. If you want to move to the next slide, we then began to look at the directivity of the patch antennas. So printed circuit boards and antennas will resonate, they'll emit at different power levels depending on the orientation at which they are measured. So the directivity of that is shown on the right. And to explain what this means to those who may not know, at 0 degrees, that's directly in front of the patch antenna, as was measured in the first test. That's where the power level is going to be the highest measured at the patch. Then at 45 degrees, you'll see that power level goes down slightly. And then at 90, it decreases even further. So changing the angle of incidence for the electromagnetic wave will change the power received at the patch antenna. You can see this modeled down in the bottom left here with these two images. You'll see that onset angle of 45 degrees for the first one and then 90 degrees for the second. And on the next slide, we can see the results of some of these measurements. The physical measurements are shown on the left. Unfortunately, we did not have a full frequency sweep for a few of these measurements, so we're only looking at the primary resonance, that 1.7 gigahertz again. And that drop in the magnitude of this measurement is shown very clearly here in our physical measurements. The blue line shows that face on, most power received, and then changing it to a 45-degree angle of incidence, we'll see that power level drops in magnitude slightly. And then changing it to 90 degrees in the green also shows a further decrease in power. With some inherent noise in our measurements, we'll see that these curves aren't all exactly the same in our physical measurements. And again, we're working to further understand the error on this. But our simulated data in EMC Plus shows a very similar drop in magnitude between those three different simulations, which marks that we are able to accurately represent the directivity of an antenna and a circuit board and understand how the power received from different angles of incidence of electromagnetic fields can change the power received at the PCB, which is, again, very promising. If we want to go to the next slide, we then tested the patch antenna within an enclosure. Testing an antenna or a circuit board on its own is useful, but knowing how they react when they're placed inside of a metallic enclosure is very useful to understand shielding effectiveness, and generally how these models will both radiate and receive power when they're protected with an enclosure. So again, the setup is shown here on the left with our enclosure. The top left photo shows that same setup with the horn antenna exciting the PCB, which is inside the enclosure. And then the EMC Plus simulation is shown here on the right. The results, again, were very promising. On the next slide, again, the frequency range response matches the physical measurements extremely well. The EMC Plus simulation hits a number of the peak frequencies along with the nulls throughout this entire frequency range. And again, while we're working to understand our uncertainty on some of these measurements, this is, again, a very promising result for a full frequency range response of this printed circuit board. We further measured a set of cables beyond just printed circuit boards. A schematic for one of these test setups is shown on the left here with a biconical antenna sending a electromagnetic field towards a 3.3 meter cable. The schematic is shown on the right and the physical setup is shown on the left. If you want to go to the next slide, we can also see the EMC Plus setup, which is maybe a little easier to take in. Essentially, we have a horizontally polarized electric field being sent towards this cable, which is stretched between two boxes and has a current probe at the top up here, which is a little challenging to see. But this basically allows us to capture both the radiated and conducted effects on the cable. The results of this can be seen in the next slide. And again, we see a really impressive frequency range response, capturing the simulated results matching the physical measurements across the frequency range, hitting both the peaks and the nulls of multiple different frequencies along this sweep here, which is, again, very promising to see. In the next slide, the further validations that we're seeking to do with this campaign is to look at some more complicated printed circuit boards, including a basic slot antenna and a couple of intentionally poorly designed basic printed circuit boards that are intended to radiate poorly, that we are then seeking to validate further and understand how those work. And then on the right here is just an image of the radiated emissions of the patch antenna, which, again, we're seeking to more robustly validate the results from in this section. So I'm going to turn it back to Tim to continue to explain the rest of these validations.
Yeah, so again, as Zach mentioned, we're not finished with validations. We'll continue to roll them out as we prepare them for the public domain. However, I do want to talk about a few other EMC environments today. This is not necessarily validation, but just ways that we can use the tools for other environments. We've talked a lot about the radiated susceptibility environment as it relates to both cables, PCBs, and enclosures. Another one that comes up quite a lot is conducted susceptibility. So in this case, there's a couple different, I would say, broad classifications of conducted susceptibility. One is the power line conducted susceptibility, the CS101 for military programs. And this is a case where unintentional emissions that happen on the one particular device's power lines may go directly through the power bus to affect other systems. The other class is usually some kind of external stimulus that can upset systems. For example, CS114 would be radiated fields that can couple their way onto conductors and then conduct their way into equipment. CS115 is crosstalk from high power switching transients on maybe vehicles or industrial equipment. CS116 looks like an electromagnetic pulse that may be from a nuclear event or man-made type of pulse. And then CS117 is a lightning-induced transient response. So either an external stimulus or just power line coupling. It is a very common approach that our customers take, and as well as our internal team. CS117, for example, you generate a current transformer that loops around the cable, and then you put a monitor probe there, and then we excite that in the CS117 case with a lightning-like induced pulse, and then we're able to see how that impacts the system. But because the current transformer is applied to the entire cable bundle, as a designer, it's a little bit challenging. For example, you may have a conductor that has multiple, or a bundle of cables that has multiple conductors within it. You don't know the induced transient on each pin. It's a very hard thing to do with pencil and paper style analysis, but this sets up very well to the EMC Plus numerical solvers. The first step that we do is represent the current transformer just by directly applying magnetic fields that will replace the current transformer. And then we separately apply a current probe. And with transmission line theory, we're able to represent the cable based on its cross section. As you see here, all of the shields, conductors, their various gauges, their impedances are represented. And so that allows us to, in some cases, minutes is all it takes to set up CS117 type of model. You can predict the voltage and currents on each individual pin of your device. And so that can be very useful to you as you are asked to design for CS requirements. This way you can determine what they are, add protection devices like commonly a diode is placed on the line that will clamp at a voltage above the operational voltage of that line. You need to understand the worst case transient so you can properly size the diode. You don't want to oversize it because it adds physical weight to your system. So every designer needs to be able to do that. Separately, for the higher frequency results, by using transfer function method, you can run a single simulation in the time domain, and you can get broadband results. So you can get the pin transient like you would for a CW test that's going to systematically step through each frequency. We can do that all at once. So it's a big time-saving process to do CS114 with a tool like EMC Plus. Radiated emissions, again, these fall into a couple types. RE101 is very low frequency, typically only used for scientific missions and things with very sensitive objects like magnetic sensors or things like that. RE102, more common in the MIL standard requirements. Essentially, the goal here is to prevent unintentional emissions from your device from jamming or impacting the performance of RF devices on a platform. This is a case study that we co-published with Intel and Ansys in recent times, where basically the goal was to predict radiated emissions of an entire device, enclosure, printed circuit board with excitations and components, all of that together along with cables. And so what Cesar Mendiz-Ruiz from Intel says, the impact was going from something that was impossible to something that is doable. So essentially EMC Plus showed that we could bridge the gap to new capabilities. So an example of some of the simulation setups. So you can pick a couple of excitations here. In this case, this is a DDR4 excitations that's used. In this case, a handful of nets. And then we can capture, in this case, just at the board level, we can look at the near fields emanating from the board. In this case, we're looking at just the 100 megahertz. And so as we are working with customer designs, understanding the excitations is a very important part of what we want to do. So if we are doing an analysis report in advance of testing to look for risk, we'll want to maybe think about picking just the worst case excitations to include. If we're doing a qual by simulation, it is beneficial often to eliminate some excitations just so that we can reduce the number of reduce the amount of work, because there may be hundreds or even more excitations in the model. So by picking only the worst case excitations, we're essentially just making the effort for analysis more reasonable. So in this case, this is just showing rendering of the radiated emissions simulation, where we have, in this case, just a single excitation on a single net that's connected to a cable. The fields exit the enclosure through the apertures in the enclosure, as well as from connections to the cable and radiating from the cable itself. And so this eventually finds its way to the antenna, and that's what we measure as radiated emissions and compare that to our limit curve. So example of what that looks like. Typically, the enclosure itself is imported from a computer-aided design, CAD mechanical design files. We can import the printed circuit boards using the electronics database format. So that's an ECAD format. Many types of board design software are able to import or export the EDB format that we can consume, and the tool will automatically assign the material properties, copper to the traces, ground planes, FR4 materials to the dielectrics, and then we're able to connect that using the transmission line theory M-harness cables, which can be shielded and unshielded, etc. When we run that simulation, we're able to extract the fields at the antenna. Typically, we convert that to dB microvolts per meter to match the standard, and then we can compare our predicted emissions of our device. In this case, this is just one excitation. So we would want to add representative excitations for everything that we think might be impactful or a risk for failing. So typically for radiated emissions, it's a balance between the engineering effort to add those excitations and the fidelity that those excitations will provide in helping us determine if there's a risk for failure in of the EMC standard. And just this shows just an animation. You can see there's two different ways that the fields exit the enclosure. You can see the apertures in the enclosure. That's a case where they leave. And if you look very closely where the cable runs left to right, you can actually see the energy reflecting, transitioning down the cable and then reflecting off the end and bouncing back. And so that's what creates that resonant mode that we see that is multiple of the wavelength of the cables themselves. And in this case, we can do radiated emissions and versus testing in the laboratory. So we can excite the cable, and then we can have the same type of broadband antenna so that we can determine the fields at the antenna. So on the left, you can see the experimental setup. On the right, you can see the setup that we have in the lab. And so comparing measurement to simulation, you can see very good correlation between simulation and testing for cables. And again, this is for a excitation of those cables themselves as they connect to the enclosure, and we're able to predict that with high fidelity. Full vehicle validation. So much of what we've talked about thus far has focused on electronic devices and then cables connecting to those devices. But in many cases, our customers are designing aircraft, cars, or industrial equipment. And the concept scales to those vehicles. I'll talk about some of the tools that we use for that. So one of the full vehicle environments that we care about is the specific absorption rate. This is the coupling of electromagnetic energy from intentional emitters to human tissues, and there's standards that must be met. In this case, there's a Wi-Fi antenna in the shark fin of this vehicle, and we're able to model the coupling of that to the human tissue and capture the specific absorption rate, the SAR coupling. Another place that we can deal with coupling is the cables themselves. So we have the ability to consume cable database software exports of files. Often that's a .kbl format that many products export. In other cases, they export XML files. We're able to consume those file types and create automatically the wiring information and map that over to the routing of the cables. The cable routing typically, not always, but it's typically contained within the CAD, mechanical design, and then the wiring information is in cable database software. So having a tool that can marry those two together is often very important. So in this case, just showing that process. So using the segment IDs that is defining all of those tubes that are in the 3D CAD, all of those should match up in the cable database software to individual segments that we can import. So with this tool, we can take that wiring diagram description in KBL, and we can map that description onto the 3D description of the cables themselves. So this is just showing what that process looks like. So what it's going to do is everywhere there's a segment in the wiring diagram, it's going to match that up to the correct cable, and it'll be able to import that. So in this case, we're going to set all of them from that external file that we imported. It says 3 harnesses available from the file. And then when we hit the next button, it will complete that import. So this is all real time. We didn't speed this up. And then you can see all of the different cables that are included there. So if we look at the cross sections, you can see there's a handful up to dozens of conductors in each segment. And so those were all defined based on the 3D engineering. So how do we use this? So all of that interconnecting cable harness now can have excitations applied to it. The same radiated emissions comments that I talked about before apply, where we want to be judicious about the excitations we apply and make sure that they're realistic and that we're picking ones that are at risk to be close to the emission limits, just because the number of excitations, there's no technical limit, but it's just an engineering time-saving limit to limit those to the worst case. So we put the excitations on the cables, and when we do so, we can predict the radiated emissions that would be at the receive antenna at various locations. And so you can see, in this case, the energy flowing among the cables and being converted to radiated electric fields. And this is just a top view of the same thing. Again, it's very clear the provenance of the emissions is coming from those excited cables and the common mode currents that are flowing on those cables. And just a quick note, we can increase the validation up to extremely complex series of harnesses. So what I showed for the electric vehicle was just a handful of harnesses, but we've proven that we can accurately do this up to thousands of conductors in complex vehicles like aircraft. This is a comparison of an experiment and simulation for a full Embraer aircraft, and it was measured with a ground measurement and compared to the conducted, the radiated susceptibility from a CS-117-like injection, and we're able to capture both the magnitude and the shape of that information within 6 dB. And this is just another validation with Airbus Defense that was published in 2021, where we predicted across a very wide range of frequencies from the tens of kilohertz up to about 18 gigahertz, and showed correlation for complex harnesses to basically a cockpit mock-up. So it wasn't a full aircraft, but it was all of the structures, their realistic cables, bulkheads, electronic devices that we're testing. Okay, so that brings us to the end of this presentation today. We had the chance to show validation of experiment compared to simulation for some devices that EMA designed and fabricated. We went to the National Institute of Aviation Research at Wichita State University into their environmental test facility, which has EMC test labs. We modified the test program so that they measured quantitative levels, and for a printed circuit board within an enclosure and an enclosure connected to cables, we cross-validated the radiated emissions from our device to the receive antenna for both the exciting the printed circuit board and exciting cables. And then we were able to do radiated susceptibility for coupling from an antenna to cables connected to a device. And we showed excellent correlation. We captured the magnitude of the peaks and the shape of the waveform in the frequency domain that we see, and saw very excellent correlation such that it would be able to predict pass or fail on a device ahead of fabrication of that device. And as we mentioned, this is the first in a series of validations that we will be presenting publicly. So if you liked this validation, please stay tuned to the webinar series for future validations. If you would like to contract EMA or collaborate in some way, please reach out. And finally, if you would like to get access to the simulation software yourself, please reach out to your Ansys sales professional or your assigned Ansys channel partner for information on getting access to EMC Plus or Charge Plus for these applications. I'm going to pass it over to Matt, and we're going to work through some questions.
Okay. Well, thank you, Tim and Zach, for that really informative presentation. I want to remind our audience members that you can submit questions through the Q&A button at the top of your display. Some questions are going into the chat. That's okay. I'll get to those, but we prefer that you submit them through the Q&A feature. So let's get started here. First question that we received: what additional validations are you considering? Will you validate conducted susceptibility and conducted emissions?
Yeah, can you say that again, Matt? I lost audio for 2 seconds.
Yeah, sure thing. So what additional validations are you considering? Will you validate conducted susceptibility and conducted emissions?
Yes. So we will be doing conducted susceptibility and conducted emissions in the future. With respect to conducted emissions, that's a very exciting case, and we're not ready to go public with it yet, but we've made some very fascinating breakthroughs recently where we have one of the biggest issues that describes both conducted emissions, which can then become radiated emissions in power systems, are where we have very fast transients happening differential mode in a power system. So that could be driving a motor or powering some external devices. Typically, that's happening differential mode. So differential mode signals, as we know, don't readily contribute to emissions that are harmful. However, because of imperfections and imbalances in the printed circuit boards and stray capacitances, other things, we have what is called differential mode to common mode conversion. And Oftentimes, if you hear EMC engineers talk about that, they say, okay, we've got high frequency fast switching transients and some black magic happens, and that becomes a common mode that is going to harmfully couple. So they know it's stray capacitance, they know it's imbalance of the line, but quantifying it is kind of not always very clear. What we have been able to do is with EMC Plus, connecting the cable harness to the printed circuit board, we've been able to measure what are called mixed mode scattering parameters for differential mode to common mode conversion. And we have been achieving excellent correlation of the of that conversion scattering parameter a priori, totally with simulation of that line. So all of the black magic of and some stray capacitance happens and we get the conversion is replaced by quantitative prediction that you can then plug into your SPICE models of your power system. So that is coming. That's very exciting. Not ready to present those results today, but that is going to be presented in the next couple months. So please stay tuned if you're interested in CE and RE from power systems like that.
Okay. Well, thank you, Tim. Next question, and this is one that I feel like we see quite a bit. What is the uncertainty in testing itself?
Yes, so that's something very important. So often as we talk about this today, you've heard us say things about correlation with the testing. Because we had the chance to make measurements in the lab, we were able to do some things that maybe you wouldn't have done in a standard EMC test. For example, we had our partners at NIAR remeasure some things on a different day with the exact same unit. And the coupling results that they showed for some of those cases were pretty different. So we're repeating those measurements and we're getting some error bars on the measurement. In some cases, it's a surprising, maybe not surprising if you've done this a while, but we're getting a surprisingly high level of variability in the experimental measurement. So that's something that we always have to keep in mind, that the experiment does have an error bar associated with it. There's a certain level of sensitivity to how things are laid out on the table, other variability in the product itself. So any discussion of simulation and experiment must consider the fact that it's correlation between simulation and experiment, and there's errors in both simulation and experiment that must be taken into account.
Okay, thanks, Tim. Next question, can we get support like documentation or literature for Python API with Ansys EMC Plus where we could use it for automation?
Yeah, that's a very important initiative we have. So at this point, our goal is to cover every feature in EMC Plus with a Python API so that if you're in a production environment, it's not enough to have a bespoke model of your device that you create by hand. We want to take our engineering design information and automate as much of the simulation process as we can. We have on the order of 80 some odd % coverage for all the product features. Our goal is to achieve 100% product feature coverage with APIs very soon. So there's a lot you can do today, and check out the documentation for those APIs. And we will, in fact, I'll switch slides if you'd like more information on that, as well as any of these other topics. We are having a user conference called EMA Expo, April 28th to May 2nd at UMass Amherst. You can go to ema3d.com/EMA-Expo-2025. One of the topics that the master's workshop will cover is APIs. So we're going to go very deep on that topic. So if someone's interested in that, that's going to be a great place to learn more about using the API.
Okay, thanks, Tim. Okay, next question. What is the difference between Ansys SI Wave and EMC Plus?
Yeah, that's a good point. So Ansys SI Wave is an independent product. It's also available from Ansys. Ansys SI Wave is focused on printed circuit boards in planar 2.5D devices where things are laid out essentially like printed circuit boards. It has EMI scanner and tools that can very rapidly assess potential problems early in your product design with very low effort. EMC Plus is a 3D simulation tool that can also model printed circuit boards, but also 3D components as well as cables connecting to them. And so EMC Plus is different. We can consume exports of boards from SI-Wave. We can also consume fields from SI-Wave if we choose to do so, but they are independent products.
Okay, thanks, Tim. Next question, can EMC Plus model/simulate an entire lightning EMP flash event, for example, component A, B, C, D, plus multiple strokes and multiple burst current waveforms, component A, B, C, D voltage waveforms, along with EMP electric and magnetic fields at 10 meters away, presumably from the target or platform. So I think what they're asking is, can we handle lightning and EMP type simulations?
Absolutely. So that's common work that people do both at the vehicle level. So looking at lightning and EMP attachment to a vehicle or illumination of a vehicle, as well as often we design the equipment with a CS116, CS117, or a DO160 section 20 or 22 test that flows those levels to the equipment. So we do have the ability to do that. The only caveat I might put is some of the multiple burst environment, there's a long lag between that second burst. So we typically model an individual burst, and through post-processing would impose when that second transient comes in, because the time is very long and expensive for simulation time. But we are able to handle both environments at both the platform level as well as the device level.
Okay. Okay, next question, and this is a pretty interesting one. I am aware of the capability of exporting the near field from SI-Wave or HFSS to EMC Plus in order to perform PCB radiation scenarios. What if my intention was to do such an analysis completely within the EMC Plus tool? The question would be, is it possible to assign active component models like SPICE or IBIS to the EMC Plus ports and run a time domain simulation?
The answer is yes. So we do have a transient circuit solver, which is the Nexum solver, same as an electronics desktop, in EMC Plus. So you can assign all of those excitations. So that's possible. And what I showed was a single SPICE excitation in that model, but there's no limit. You can add more. The only limit is the time required to add each excitation at the correct location in 3D.
Okay. Back around slide 21 or 22, a question came in about the types of probes that you're using to measure the power received and where those probes were placed. Can you skip back to that part of the presentation? Yeah, I think it was around there. So yeah, they're asking, what are the types of probes? I assume in the measurement, and where they were placed in the measurement.
So I believe that within the enclosure themselves, they are coupled, I think, likely to a network analyzer. But I don't know off the top of my head. If Zach's still on, maybe he knows what the probe is inside those enclosures.
I'm also not as aware of the physical measurement one, but I'm happy to talk about the EMC Plus ones a little bit more. I was more part of the printed circuit board measurements, and the cables were some other experts in the company as well. But
okay, that's fine. We can
yeah.
track that down and respond to the question offline.
It should also, I think, maybe be back in the schematic. I'm not positive, which is one slide before this, I believe. It might be, yeah. But Matt, as you said, we can tag up later.
Yeah, so thank you for the question, audience member. We will follow up with you after this. And we are at the top of the hour. Tim and Zach, any final comments here, or we will wrap this one up?
No, I'll just return to the EMA Expo slide and just note if anybody is interested in learning more or joining the master's workshop, this is a great place to go deeper.
Yes, certainly. It's a great continuing education opportunity, a great networking opportunity. We encourage all of you to attend, and we look forward to seeing you there. Okay, so as a reminder, and there were some questions that we were not able to get to today, so we will address those via email and get you answers. You'll also get an email from us with a link to the recording of this presentation. I know a few people asked about that, and it will also be posted on our website, so you'll be able to go back and watch it or forward it to your colleagues. Next up in the EMA Solving Electromagnetic Challenges webinar series is Ansys EMC Plus and Ansys Charge Plus, What's New for 2025 R1, which will occur on March 19th. You'll want to watch this one. We have a lot of exciting new features coming out in both products. So please get registered for that webinar, and we will see you on March 19th. Thank you for your time and attention today, and we hope you have a great rest of your day.